is by Dan Nix from the University of Nottingham. Dan is going to talk on orbits and bungee sets. Thank you, Dan.
Okay, so yes, orbits and bungee sets, and really it's almost two short talks, one about orbits and one about bungee sets. Let me get on to my next slide. Okay, so the first part will be all about orbits, and here we'll do something a bit unusual. So normally when we do study discrete dynamical systems, we fix a function and then we study the orbits that you get when you iterate that function. What we'll do for a while is turn that around completely. So we'll say, if we're given a sequence in some space, then can we find a function for which that sequence is an orbit? So can you generate that sequence by iterating some function? So that will be the first part of the talk. And the second part of the talk will be doing things the traditional way around. So we will look at bungee sets. So given a function f, the bungee set is the set of starting points for which, when you iterate, the orbit has both bounded and unbounded subsequences. Or in other words, the orbit is not bounded, but also does not tend to infinity. And throughout, we will be interested sometimes in quasi-regular maps on d-dimensional real space. So let's get stuck into the first part. So our guiding question throughout is, which sequences are orbits? So as I said, here we will start off with a sequence, which might be a sequence of points in the complex plane. We might call it Zn, or we might have a sequence of points Xn in R to the D. And the general question is, does there exist a function that realizes that sequence? So that's my terminology for, does there exist a function for which the given sequence is an orbit under iteration of that function? Or maybe to put it more clearly, can you find f? So given a sequence, can you find a function f that maps Z0 to Z1, Z1 to Z2, Z2 to Z3, and so on? And then if you can find such a function, is the function unique, or are there others? I should have mentioned at the start, all of this is joint work with Dave Sixsmith, and I have to thank him for coming up with the interesting questions that I'm going to tell you some answers to today. So it is pretty quickly evident that not all sequences are orbits. For example, if you were given the sequence 1, 2, 1, 3, and so on, that sequence can't be the orbit under any function, because if 1 gets mapped to 2, 2 gets mapped to 1, and then 1 can't also get mapped to 3. 1 can't be mapped to 2 and also mapped to 3. So that sequence is never an orbit under any kind of function. Otherwise, the answers we get to these questions of existence and uniqueness might depend on what kind of functions we're going to consider. So we might just look for a continuous function that realizes a given sequence, or we might be interested in polynomials or transcendental entire functions on the complex plane, or we might be interested in quasi-conformal or quasi-regular maps on R to the D. They sit somewhere in between the continuous functions and the analytic ones. So if we spent a few moments thinking about what goes wrong with this 1, 2, 1, 3 sequence, we could pretty quickly write down a necessary condition that a sequence must have for there to be any chance that it's the orbit under iteration of some function. And then if we thought a little bit harder, we could write down a necessary condition that a sequence must have for it to be an orbit under a continuous function. And if you tried to do that, then I think reasonably quickly you would end up with the following definition. So here we will say that a sequence of points Xn is called a candidate orbit if it has the following property. So the property is, suppose there's some point X in your space, and there's some sequence of integers nj such that some of the terms in your sequence are converging to x. Then there has to be another point x prime, so that when you look at the next, you take your xnj and you look at the next terms in your sequence, they should converge to X prime. Okay, I didn't do that well. So the idea is if you have something like a subsequence which converges to some value, then when you look one step on from your subsequence, it should converge to something else. And this X prime should only depend on X. Yeah, my computer's telling me I need to restart, so things may continue to go wrong. Okay, here the NJ, this XNJ doesn't have to be a subsequence. So for example, this could just be a constant sequence of terms. And in that case, what the definition is saying is that to be a candidate orbit, it must be true that if ever two of the terms in your sequence are the same, then the next terms must be the same. So the terms after must be the same, and so on. So in other words, if your sequence visits the same value twice, it must become periodic from that point on. Okay, so I claimed that that is a natural sufficient condition for a sequence to be realized by a continuous function. And our first theorem says, when I can get to it, that in fact this condition is necessary and sufficient. But my slides are not scrolling. There we go. Okay. So here the theorem here says a sequence of points xn satisfies this candidate orbit definition if and only if there is a continuous function that realizes the sequence. So that completely settles the existence question if we're interested in continuous functions. And in fact, we can settle the uniqueness question as well. So the function you get, f, is unique if and only if your sequence of points you started with is a dense subset of space. So it is, I think, fairly clear that if you started off with a sequence that was dense in space, then there can only possibly be one continuous function that realizes that sequence. And it's also fairly clear that if your sequence misses out some open set, then by changing your function a bit on that set, you could generate lots of different functions that realize the sequence. Okay, so with that theorem, that's a complete answer to our question if we are interested only in continuous functions. So what we'll do is move towards trying to answer the question, which sequences are orbits under entire functions on the complex plane? And before we get there, it's useful to have some fairly simple terminology. None of this will be a surprise here, but we say that a sequence of points Zn is bounded if the modulus of all the terms are bounded above. We'll say that a sequence is escaping if it tends to infinity. We'll say that a sequence is bungee if it is not bounded and not escaping. Or another way to say that would be it's got a bounded subsequence and also an unbounded subsequence. And finally, we will say that a sequence is periodic. And my slides are not cooperating again. So periodic definition is the obvious one, except that I will include pre-periodic sequences or eventually periodic sequences. I'll just call those periodic. But we are going to need another slide here. There it is. Okay, so the question is, which sequences are orbits under entire functions on the complex plane? And entire functions are certainly continuous, so a necessary condition is that our sequence must be a candidate orbit. So suppose we've got a candidate orbit, then it must be one of the following types. So there are 4 different cases here. So case A is periodic orbits, so that includes everything pre-periodic, I count as periodic, escaping, bungee, or bounded but not periodic. So every candidate orbit fits into exactly one of those categories, And now we will try to answer the question of, can you realize that kind of sequence with an entire function? So in case A, if you write down a periodic sequence, then you will be able to realize that by infinitely many different transcendental entire functions and also infinitely many different polynomials. Okay, case B, what if you started off with an escaping sequence, so a sequence that tends to infinity, and your question is this the orbit of some entire function? Well, the answer in that case is that there will be infinitely many transcendental functions that realize that orbit, and there might also be a polynomial, but if there is a polynomial, there's only one of them. Case C, what if you write down a bungee sequence? Well, in that case, it might be realized by one entire function, but if it is, it must be a transcendental entire function because polynomials never have bungee orbits. Right, for a complex polynomial, once you get near infinity, you're in the attracting relation of infinity and your sequence has to tend to infinity. So polynomials don't have bungee sequences. So there's one case left. What if the sequence you started with was bounded, but not eventually a periodic sequence? Well, in that case, your sequence might be realized by an entire function. That function might be a polynomial or it might be a transcendental function, but if there is one, it's unique, certainly. So I guess what we can remark is that the question of uniqueness is settled, because in each of these cases, either there are infinitely many functions that could realize your sequence, or there is at most one function. So uniqueness is done, but the existence question is still open in a couple of cases. So for polynomials in cases B and D, we're not sure about uniqueness. And for transcendental entire functions, the existence question is open for bungee sequences and also bounded sequences that aren't eventually periodic. So what is it that's special about these cases that are left open? Well, these are the cases where there's a finite accumulation point that you have to deal with. And if you're trying to realize a sequence that accumulates at some point in the plane, then we shouldn't be surprised that that is difficult if you're trying to do it with an analytic function, because analytic functions are very rigid. Right? We have the identity function, we have the identity theorem, sorry, and we have Taylor's theorem, and this gives us a lot of local information about how analytic functions have to behave. So it's very difficult to realize a sequence with an accumulation point with an entire function. So in fact, you could write down lots of necessary conditions for these kind of sequences to be realized. And this is something we did. If you look at the Taylor series and analyze the Taylor series, you can write down countably many conditions that a sequence would have to satisfy for it to be realizable by an entire function. So really my feeling is if you write down a sequence that has an accumulation point, it will not be the orbit of some entire function unless the way you wrote down the sequence was by iterating an entire function in the first place. Otherwise you won't be able to do it. So here are some examples of why this is difficult. So from now on, we'll just move to the special case where we're talking about sequences tending to zero. So they certainly have a finite accumulation point. I don't want my sequence to ever be zero, but it should tend to zero. And here are some examples that we can't realize by an entire function. So this first example is the sequence 1, a half, a quarter, and so on. And the pattern here is that each term is the square of the previous term, except that a half is not 1 squared. So what happens if you're going to come up with a function that maps a half to a quarter and a quarter to a 16th and 1 over 16 to 1 over 256, and you want that to be analytic, then the only possibility is that your function is z squared, but z squared doesn't realize that sequence because 1 squared is not a half, so it breaks at the first step. So it's almost failing for a trivial reason, but it gives you the idea that it's very hard to realize these sequences. Our second example is a variation on this theme. So it's almost the sequence, a half, a quarter, a 16th, and so on, squaring each time. Except that now we're going to add on a very small positive epsilon, and these epsilons will tend to 0 fast. And again, what you can show is that if that sequence was going to be the orbit under some entire function, then the entire function would have to be z squared, but actually z squared doesn't work. And in fact, it fails at every step if the epsilons are going to 0 fast enough. And then our third example is a slightly different flavor. So here, if q is a non-integer real number that's bigger than 1, and you take the sequence given by a half to the power of q to the n, then that sequence can't be realized by an entire function. So what's happening here? If q was an integer, this would just be the orbit of a half under the map z to the power q. But I'm now choosing q not to be an integer, and I claim that there's no entire function that would generate that sequence. And you can say that by thinking about the Taylor series, because if there was an entire map, you'd look at its Taylor series near 0, you'd look at the first term, it would have to be some multiple of z to some power. And if you evaluate a couple of limits, you find that that power would have to be equal to q, but if you've chosen q not to be an integer, then that can't work. Okay, so the moral of this part of the story is that analytic functions are in general too rigid a class to try to realize sequences that have accumulation points. So then that leads us to look for a more general class. What if we introduce a bit more flexibility in our functions? Then maybe we'll be able to realize more different sequences. So our question now is, what can we do if we're going to think about quasi-conformal or quasi-regular maps? And the sneak preview is that if we're going to allow ourselves to think about quasi-conformal maps, then we can realize all three of those examples on the previous slide. So as I'm about to talk about quasi-regular maps, I should give a very brief introduction. So this is almost all I'm going to say. A quasi-regular map from R to the D to R to the D is a continuous sense-preserving map that sends infinitesimal spheres to ellipsoids of bounded eccentricity. So of course, analytic functions send small circles to small circles. What a quasi-regular map does is allow a small amount of stretching so that the major axis here is a bit longer than the minor axis, but there should be a uniform bound across space on how much stretching is allowed. So quasi-regular maps like this generalize analytic maps on C. And this generalization happens in sort of two ways. Even if you're just interested in the plane, quasi-regular maps are more general than analytic maps. But also quasi-regular maps allow you to move up and do things in higher dimensions when these things can be kind of analogous to analytic functions on the plane. Okay, a couple of remarks here about quasi-conformal maps, because I think people are more familiar with quasi-conformal maps than quasi-regular maps. The only difference is that quasi-regular maps are injective and quasi-regular maps don't have to be. And the last bullet point here just states the fact that quasi-regular maps on the plane can always be decomposed into an analytic map composed with a quasi-conformal map. So where are we going next? We're going to stick with our special case of sequences that are tending to 0. And the question is, if someone gives us a sequence tending to 0, can we find a quasi-regular map for which that sequence is an orbit under the quasi-regular map? And we're going to state a necessary condition, and then after that, one sufficient condition. So here is a necessary condition. So what we're saying is, if you've got a sequence which tends to 0, it must satisfy this condition for there to be any hope that that sequence is an orbit under a quasi-regular map. So let's have a look. So suppose Zn is a sequence tending to 0 in R to the D. then for there to be any chance of it being realized by a quasi-regular map, there has to exist a mu, a nu, and a c, such that for all large n, these two conditions hold. They're not as bad as they look at first sight, because the first one should apply whenever the n+1th term in the sequence is smaller than the nth, and the second term should apply whenever you're sort of stepping away from 0. And what do these conditions say? Well, they're just comparing the ratios of the moduluses of successive terms. So this condition is saying that the ratio between two successive terms is bounded above and below by powers of the ratio of the two terms before. So if you look at the successive ratios, they shouldn't jump around too wildly. Okay, so that is a necessary condition. Your sequence must do that if you hope to achieve it using a quasi-regular map. Ideally, we'd like a condition that's necessary and sufficient. We haven't got that, but we can get kind of close. Hopefully, if it will appear. So when it appears, there'll be a sufficient condition which works only on the complex plane. So the necessary condition there works in d dimensions. The sufficient condition we have only works on the plane. And it's not appearing, so but I can describe it and it will appear in a moment. There it is. What fun. Okay, here it is. So suppose you have a sequence of points tending to 0 in the complex plane. Suppose that our necessary condition holds. Right, if you're looking for a sufficient condition, it's fair play to assume the necessary condition. So assume that there's a mu and a nu and a c such that this first thing holds. And also assume now that our sequence we're looking at is decreasing in modulus. And in fact, a bit more than that, assume that at each step in the sequence, the modulus goes down by a factor of at least d, where d is some number less than 1. Well, then in that case, the sequence definitely can be realized by a quasi-conformal map on C. In other words, that sequence is an orbit under a quasi-conformal map. The proof of this is an explicit construction. So we just move to logarithmic coordinates and write down appropriate piecewise linear maps. And we show that we can build a quasi-conformal map that realizes sequences that satisfy this condition plus this necessary condition. And it's kind of a bonus, right? They're realized by quasi-conformal maps, not just quasi-regular. So let me make 2 remarks about this. The first is that this sufficient condition is good enough to handle those 3 examples we saw earlier, which you couldn't get by using entire functions, but you can get all of them by using quasi-conformal maps on the plane. And our second comment answers an obvious question. If you try to replace the bit of that theorem that said that the terms at each step have to get smaller by a factor of d, if you just try to prove the same result for sequences which were strictly decreasing in modulus, then that theorem fails. So we can write down a counterexample, and the way we do that is just by coming up with a sequence which has strictly decreasing modulus. It satisfies the necessary condition, but we can construct this sequence in such a way that it can't be realized by any Holder continuous function. And quasi-regular maps always need to be Holder continuous. Okay, that is the end of part 1 on orbits, and we'll move on to talk about bungee sets in part 2. So now we're going to do things the traditional way around. So first of all, we'll fix our function f, and then we look at the orbits generated by that function. And our space might be the complex plane, or it might be r to the d. And in either case, we can partition the space based on the behavior of orbits in a possibly familiar way. So we have I have three sets. The first of them is just the escaping set. So that's the set of points which go to infinity under iteration. Our second set of interest is the bounded orbit set. So that's the set of points whose iterates always stay bounded. And if you were talking about an entire function, you would probably denote this by k of f. You might call it the filled-in Julia set. Unfortunately, if you might be talking about quasi-regular maps, then k of f usually denotes the dilatation. So instead, I'll use this notation BO, bounded orbit set of f. And then the third part of our partition, the bungee set, that's everything else. So it's points whose iterates don't tend to infinity, but they don't stay bounded either. Or in other words, there's a subsequence of the iterates that tends to infinity, but another subsequence that stays inside a bounded region. So within complex dynamics, it's the first two sets on this list that have had more study and a longer history, but there's also been a little bit of work done on the bungee set of analytic maps. I should say something about polynomials, right? For a polynomial, the escaping set is just the attracting basin of infinity, and there aren't any bungee points. So the bungee set's always empty for a polynomial, but for a transcendental function, there always are some bungee points. So one way to see this is if you know that there are points that have a dense orbit in the Julia set, those points will have to be bungee points. Okay, the first people to study the bungee set as a sort of set in its own right in complex dynamics were John Osborne and David Sixsmith. And one of the things they showed is that the boundary of the bungee set is the Julia set. Okay, it's also now well known that it was proved by Eremenko that the boundary of the escaping set is the Julia set. And once you know that every point in the Julia set's near an escaping point, and you also know that periodic points are dense in the Julia set, then you see that the Julia set is also the boundary of the bounded orbit set. So we have this partition of the plane into three different sets, and the Julia set is the common boundary of all of them. So that's a nice situation in complex dynamics. And the question now is, what can we say about the bungee set and these other sets if we're interested in iterating quasi-regular maps? Well, at least these definitions work just as well for quasi-regular maps. It's clear what it means for a sequence to tend to infinity or for a sequence to stay bounded. I should say something about what's the right analog of a transcendental function when we talk about quasi-regular maps. And I should say something quick about what's the analog of the Julia set for quasi-regular maps. So that's what we'll do here. So a quasi-regular map is said to be of transcendental type if it has an essential singularity at the infinity, by which I just mean that the function doesn't tend to any limit as x tends to infinity. Okay, I won't say anymore. There's a very naturally the analog of transcendental entire functions on the plane. So how about the Julia set? Well, first of all, let's go back and think about Julia sets of entire functions for a moment. One way you can characterize the Julia set of an entire function is as the set of points with the blowing up property. By this, I mean the Julia set is the set of points Z that have the property that if you take any neighborhood U of Z, then if you look at the union of all the forward images of that set U under iteration, that union blows up to cover the whole of the complex plane apart from a finite number of points. So the points in the Julia set are precisely the points with that property. So that's well known for entire functions. For quasi-regular maps of transcendental type, we will use this as our definition of the Julia set. So for trans-type quasi-regular map, we define the Julia set as the set of all point x with the property that if you take any neighborhood U of x, then when you look at all the forward orbit, you look at the forward orbit, all the forward iterates of U under your map, that blows up to cover the whole of space apart from a small set. So there might be a small set of points that missed out. And whereas before our small set was a finite set, now our small set would be a set of zero conformal capacity. Okay, so this is not as pretty as the entire version, but one of the reasons that we're having zero conformal capacity there is it allows us to show that the Julia set is always non-empty and completely invariant. So we can show that for any transcendental type quasi-regular map, there always will be points that have this blowing up property. Complete invariance is easy to show. It would be much nicer if this set is finite, rather than talking about conformal capacity, which I'm not going to talk about. It's just a small set. In fact, if you are only interested in working in the plane, then it's equivalent. You can replace this capacity thing with just blowing up, missing out a finite number of points. It's the same thing if you're just working in 2 dimensions. Also, if you're working in 2 dimensions, we can show that the Julia set itself is not a small set, which is nice to know. I mean, maybe even this Julia set contains continua. That's possible, but not proved. And actually, the conjecture is that these things hold true in any dimension. So if you're an optimist, then hopefully the Julia set is a set of points that have this blowing up property where only a finite number of points get missed out. Okay, so that was a quick introduction to what Julia set means for quasi-regular maps. And now we'll state a few results about dynamics of quasi-regular maps. So first of all, Siebert proved that a transcendental type quasi-regular map has always got infinitely many periodic points. So in particular, there are always infinitely many bounded orbit points. So the bounded orbit set is always non-empty. Bergweiler, Fletcher, Langley, and Mayer showed that transcendental type of quasi-regular maps always have escaping points. There's always a point whose iterates go off to infinity under iteration. So the escaping set's non-empty. And thirdly, Walter Bergweiler and I showed that the Julia set will always be a subset of the boundary of the escaping set, and it will always be a subset of the boundary of the bounded orbit set. But unlike in the entire case, you can't necessarily put an equals there. There are examples to show that this might be a strict inclusion. So that was the state of play a year or 2 ago, and that leaves open the question of what about the bungee set for quasi-regular maps? And Dave and I were able to prove something. So we showed that if you have a transcendental type quasi-regular map, then there's always a bungee point. In fact, there are always bungee points in the Julia set. And of course, once you've got one, you've got a whole orbit. So once you've got one, you've got infinitely many. And the second bullet point here, we can also show that the Julia set is contained in the boundary of the bungee set, at least under this condition that the Julia set itself isn't too small, but that condition is definitely satisfied if you're in the plane, and it's conjectured that this is always true in any dimension anyway. So it's not a strong condition, I think. Okay, for entire functions, that inclusion is an equals, but maybe we don't expect an equals here for quasi-regular maps because we didn't get an equals there either. So what I want to do next is draw a picture to give a quick sketch proof of why the bungee set is non-empty and why the Julia set is contained in the boundary of the bungee set. Right, so I'm going to lay you flat so you can look at my ceiling. So we're going to try and prove that the Julia set is in the boundary of the bungee set. And the first thing we do, which I'm not going to go into, is just show that if you pick a large number R, then neither the part of the Julia set in some big ball nor the part of the Julia set outside some big ball has got zero capacity. So that's just claiming that there is a reasonable amount of the Julia set near the origin, and there's a reasonable amount of Julia set near infinity. And then what we do is we will aim to use the blowing up property to show that if we take any neighborhood of a point in the Julia set, then we can find a bungee point somewhere in that neighborhood. So I want to get drawing now. So, oh, okay. So that in black is a bit of Julia set. And let's suppose we take some open set U, which meets the Julia set. And I want to try and find a bungee point in there. Well, let me draw around here a large ball. So say that's a set of points with modulus less than R. Okay. And let's also think about points with big modulus, so bigger than big R. And what we said in the first bullet point is that there's definitely a reasonable amount of Julia set up here somewhere. Okay. It feels like the technology is going to give up in a moment, but we'll try. So what we then do is think about what the blowing up property tells us. So it tells us, because this meets the Julia set, if we iterate forwards starting from U, then the images blow up to cover the whole of space apart from a small set. So in particular, what we should get is that when we iterate forward starting in U, it will definitely hit a point of the Julia set of large modulus, which I'm trying to... My technology is struggling. So either it will catch up in a moment, or I'll have to give you a verbal description of some kind. Okay, so when we iterate forwards from U, eventually we hit some big point in the Julia set. So after some large number of iterates, there is a point in U that gets mapped out there. And then we just play the same game again. So I take some neighborhood around that point of the Julia set. The blowing up property tells us that if we keep iterating forwards, we'll hit almost everything. So in particular, we'll hit a point down here somewhere in the Julia set. So there's a point in that neighborhood that gets mapped down there after some large number of iterates. And then we do same again. Take some neighborhood of this. Now, let's think about points with slightly larger modulus. And applying the blowing up property on here tells us that there's definitely a point in here somewhere that gets mapped somewhere out here and under a bunch more iterates. Okay. And then we apply a pullback argument. And if we pull back in the right way, what we find is we get a point in the Julia set here that first gets mapped up here. So it gets mapped big, and then it gets mapped small again, and then it gets mapped even bigger, and so on. So that will be a bungee point in the Julia set, and also in that set U that we started with. And then, okay, I think I'll skip the rest because I'm running out of time slightly. So because U was an arbitrary set, what you've shown there is that the Julia set must be contained in the closure of the bungee set. And then because of the previous results, we know about how the escaping set compares to the Julia set. Actually, you can get this fact. Once you know there are bungee points near any point of the Julia set, and you also know there are escaping points near any point of the Julia set, then the Julia set must be contained in the boundary of the set of bungee points. Okay, that's enough sketching of that proof. So what we were proving there is that the Julia set is contained in the boundary of the bungee set. Might it be true that you can put equals? No, it's not true. So we can construct an example of a transcendental type quasi-regular map whose Julia set is a proper subset of the boundary of the bungee set. And the way we do that is by first constructing a quasi-conformal map of the complex plane that has bungee points. And this is a sort of a surprising result, because if instead of thinking about quasi-conformal maps, you were to think about conformal maps from the complex plane to the complex plane, well, then you'd just be thinking about affine maps, right? Z goes to AZ plus B, and these maps have very boring dynamics. They certainly wouldn't have bungee points. And yet, if you allow yourself to think about quasi-conformal maps instead, then we're saying that you can have bungee points for quasi-conformal maps. So the idea in the last few minutes is to first give a quick picture of how we build a quasi-conformal map with bungee points, and then to say how we can use that to come up with a transcendental type map whose Julia set isn't the boundary of the bungee set. So here we will have a very quick picture of how we build our quasi-conformal map that's got bungee points. So we start off by drawing something that's almost a vertical strip, except that it gets narrower and narrower as it goes up. So call that set T. And then we have an explicit formula for a quasi-conformal map. I'm not going to give you the formula. So this will be a map from T to T, which is the identity on the boundary. And inside, well, if you took a point on the imaginary axis, all points on the imaginary axis get moved up a little bit. So if you start on the imaginary axis and iterate, you would escape up to infinity. So if you start at some point I times y, and those iterates will escape to infinity. Okay, and as I said, that's a short explicit formula for that function g, but I'm not going to give it to you. It's not interesting. The interesting bit is this set T we call a straight snake, and what we do next is hit it by a quasi-conformal map to map that straight snake T onto what we call a coiled snake. So let me draw the image of T under this QC map phi. So it starts off looking the same, goes up for a bit, and then it bends around and comes back down. And all the while it gets thinner and thinner, but then it goes up again, and it goes up a bit higher than it went last time, before it comes back down again, getting thinner and thinner. And then it turns around, and then it goes up higher than it did the time before, and so on. And because it gets thinner and thinner all the time, we can put infinitely many coils in and still keep everything in a region of finite width. And then we define our quasi-conformal map of the plane, the thing we were really after. Well, on that coiled snake, we just define it to be phi composed with g composed with phi inverse. So that's how it is on the coiled snake. Inverse. And everywhere else is just the identity. So what's the effect of this? Well, the important thing is there are certain points in the middle, which when you iterate this big F, because you just move back to the straight snake, move up the imaginary axis, and then move back to the snake, you get points. I hope this is clear from the picture, that move along the coiled snake, move along the middle like this, under iteration of big F, and these are bungee points, because infinitely often they come back to this bounded region here, but also as they go through the tops of the coils, there's a subsequence of iterates tending off to infinity. So by coiling up our snake, we get a quasi-conformal map with bungee points. And then the final thing I want to show you is how do we use that construction to build a transcendental type mapping for which the Julia set is different from the boundary of the bungee set. And here we'll just have a quick picture. I'm going to build up the function bit by bit. I will write h for the upper half plane. But first of all, let's define our function for when the imaginary part is less than or equal to -1. And down there, our function is just z plus a small multiple of the exponential of minus z squared. So that's analytic, actually, isn't it? And right, why do we choose this? This exponential bit means the function grows very rapidly as you go down the imaginary axis. And this will guarantee that our final function is transcendental type. So the exponential bit will guarantee transcendental type. The next step is we say we want our function to be the identity on the real axis, and we interpolate in between. And if delta is small, we can do this, and we can do it in a quasi-regular way. So far, this construction is the same as an older one by Walter, but now I can do something different with it, because we've basically got the whole upper half plane to play with, and we just need to be the identity on the real axis. And what we'll do is we'll drop our snake into the upper half plane. So in most of the upper half plane, our function is just going to be the identity map, but then there's also going to be this snake where we get this bungee dynamics going on. So that is a quasi-regular map, and it's transcendental type, and the claim is that the Julia set is different from the boundary of the bungee set. And the reason for that is if you look at the upper half plane, the upper half plane gets mapped into itself. Because in most of the upper half plane, our function is the identity, and the snake gets mapped into the snake. So the upper half plane is being mapped into the upper half plane. So there's no blowing up going on in the upper half plane. So there aren't any Julia points in the upper half plane. But on the other hand, there are bungee points, because there are bungee points in here. And there are definitely lots of points that are bounded, because the function is the identity everywhere around here. So the boundary of the bungee set intersects the upper half plane, but the Julia set doesn't. So those two sets must be different. Okay, we did have a name for this sort of construction, the function we get by drawing this sort of picture, which I suggested as a subtitle for the paper, but Dave, my co-author, wasn't so keen on it, but I like to call this the snakes on a half plane construction. So there, I've gone over, so I'm sorry for that, but I am finished now. I can see Lasse laughing, which is nice.
That's done. Are there any questions or comments?
Dan, so in your orbits theorem, you were saying that some of you would say most sequences are not realized. I mean, is there any way? I mean, I guess there are probably various ways of making that precise, because all you really need, once you have one accumulation point, that already determines which function you would have to have if it was entire. So I guess the other sequences. But I mean, is there any kind of sensible way of making that statement precise that doesn't make it obvious? And I guess in the case of polynomials, I mean, I guess again it's kind of clear that you have a sequence going to infinity. Most sequences are not realized by polynomials, even if they have the right asymptotics for z to the d, because you only have a finite dimensional, you only have finite parameter family of polynomials of the given degree. And you can move your points kind of as much as you want.
Yeah, if you had a sequence that works and you move any one point, it definitely doesn't work anymore. Yeah. And so we write down loads of conditions that say your sequence must satisfy all these things if it's going to work. And they're just so restrictive that it's just not going to happen in general. We didn't have a nice killer way of summing it up.
For quasi-regular maps, so I guess, I mean, you have this thing about going to zero, and obviously you have some kind of local already. You have some local conditions that you need, which you're kind of describing there. Is there any sense in which you only have local conditions, or do you know what I mean? So if you kind of know, I mean, let's assume for a moment that the orbit is kind of, you have a discrete point and then you have some accumulation. You have a discrete set of derived points of the orbit or something like that, right?
Right.
So is there any sense in which, if you kind of know that you can realize it kind of locally near every one of those points, that you can then somehow glue it together to a global quasi-regular map? And what if you end up having accumulation set the whole, the whole space? Would there something like that still be true, or probably
Right.
not actually?
So my guess is sort of what you say. If it was a discrete set of accumulation points, then you might have a chance. But in general, probably not.
I guess not. Yeah.
Any more questions for Dan?
Can I ask one,
Sure.
Russell?
Yeah.
That's great talk, Dan. Thank you very much. Is there some? I mean, I seem to remember there's with the fast escaping set instead of the escaping set, you get a nicer result related to the Julia set. If I'm right, is there a variation of the bungee set that might give you a equality result? Just a kind of wild thought.
Points that sort of escape off quickly for a while and then come back.
Well, I'm not sure, but
I don't know. Yeah, you're right. For transcendental type quasi-regular maps, it remains true that the Julia set is exactly the boundary of the fast escaping set. I don't know what fast bungee might mean.
Well, I didn't dare to say that out loud in case it was complete nonsense, but
maybe there could be.
Yeah. By looking at your examples and working out what you shouldn't happen or something like that. It's just a thought.
Yeah.
Very nice talk.
Any more comments for Dan? Yes.
So I have more like a comment than a question. So regarding the orbits, so the question whether they can be realized or not, years ago, I thought about a similar question, although for automorphisms of C2, where the situation is slightly, of course, different, even with the sort of what you would expect with the most, the easiest case. You have a discrete set and you would like to say whether or not there exists an automorphism for which this set can be realized as an orbit. And there are pathological examples of discrete sets in C2, for example, for which you know that the only automorphism which maps this set into itself is an identity. But there are certain sets which are called tame sets, which were defined by Rosé and Rudin. And for those, you know that they can be realized as orbits of automorphisms. So my question, which I was trying to think about it, but I never succeeded, is whether every orbit of an automorphism, suppose it's a discrete orbit, if it's tame. So just sort of if somebody eventually wants to think about this question. Thank you.
Okay, it's nice to know that someone else has thought about these things before.
So I guess I just want to say I think Snake on a half plane is a pretty good title. So I would approve of that.
Okay, maybe we should thank Dan again for a great talk.